Swayam Prabha. Digital India. Educated India.
Welcome students to this class. In today's class, we will continue our discussion on the postulates and principles of quantum mechanics. So far, we have discussed three different postulates of quantum mechanics. The first postulate said that the state of a quantum mechanical system is completely specified by a quantity that we call wave function. The wave function has all the information about the state. And postulate 2 said that if you want to obtain an idea about any classical observable, quantum mechanics provides us with all the quantum mechanics provides us with the required operator corresponding to that classical observable. This is that postulate 1 and postulate 2, and in postulate 3 said that if we apply this quantum mechanical operator on our state function, the only allowed observables that would come out of the experiment are going to be the eigenvalues of this operator. Since these eigenvalues are going to be the outcome of an experiment, we suppose that they would be all real quantities. So, if eigenvalues are real corresponding to this operator, quantum mechanical operator A, then we discussed one important consequence, that is the operators who have eigenvalues real would follow a necessary condition. Those linear operators which have real eigenvalues follow a condition with which we call them as Hermitian operator. The general definition of this Hermitian operator we discussed in our previous lecture is that if I have if I have two well behaved function f and g, and the right hand side is f star, the complex conjugate of a operator a, g another well behaved function. If I do this integration over all the space, only Hermitian operators would fulfill this equality. This is the condition for which we call any linear operator as Hermitian operator. A in this case is an Hermitian operator. If a operator A satisfies this condition for any f and g as two well behaved functions. Please note one important thing is that in the left hand side, the operator A acts on function g. In the right hand side, this has turned over. Operator A is actually acting on function f, not on function g. Of course, after we have now a function out of this operation, and then we can multiply that with another function and then do the integration. But important thing to note is that in the left hand side, the operator A acts on function g, on the right hand side the operator A acts on the function f. This is the condition for Hermitian operator. Now, we would actually take a few examples and see whether these operators are Hermitian operators or not. Our first example, we know that operator P x is given by minus I h bar d by dx. This is the functional form of the operator, and now we will check whether this is Hermitian or not. We would write down the general formula to check whether the operator is Hermitian or not. Now, we would use we will define any well behaved function, and since the variable is here x, so I take x from minus infinite to plus infinite, and I evaluate this integral. I say this region is my operator. So, I say this minus I h bar is constant. So, I take it out of my integration. Now, to solve this integral, we will use the integration by parts rule. I am sure you all are aware of this technique from your mathematics courses. If I have a function u dv and I want to evaluate its integral between the limits a and b, the integration by part says that I can take the product of u v and evaluate the value at these two limits u v at a and b minus v d u. So, in this term here, so I define u as psi star as my u, and I define psi as v. So, here if you see, then the form of this expression is that u dv, because this is d psi by dx. So, therefore, I can now use this formula over here. I have minus I h bar, I have to evaluate u v, u is psi star, v is psi, and I have to do this evaluation at the two limits minus infinite to and plus infinite minus v du. V is psi, du is now d psi star by dx, and I have to integrate this. So, this is what I get when I use the integration by part. When I look at the first term here, this term, you see that I have to do this evaluation of psi star psi at minus infinite and plus infinite. What happens to the wave function at minus infinite and plus infinite? If the wave function remains finite as x goes to infinite, then we have a problem. The problem is that this wave function is not well behaved function, it is not square integrable. So, therefore, it will not be an acceptable function. Since we have started the discussion by telling that we are dealing with some well behaved function. So, therefore, psi as well as psi star have to become 0 when x goes to minus infinite or plus infinite. So, at limit x minus infinite and limit at x plus infinite, these psi and psi star, therefore, psi star psi, the probability have to become 0. So, for any well behaved function, this condition is given. So, if this term is 0, then I am left with the term, I have a minus sign here, I have a minus sign here to take care. So, I take this I h bar now inside the integration. What I did is that I take plus I h bar into this integration and then write minus I h bar with a complex conjugate, then that gives me I h bar. And when I look at this, the right hand side, you would see that I have shown the right hand side of the Hermitian operator condition is fulfilled. So, if you compare the left hand side here and the right hand side, you see that the p x operator is actually a Hermitian operator. We would use the similar argument to show that kinetic energy operator is also a Hermitian operator. If you remember, the kinetic energy operator T, or sometimes it is given as k cap, is the functional form of this operator is. To show that it is a Hermitian, we start from the condition that psi star minus h square by 2 m where x goes from minus infinite to plus infinite. This will be the right hand side of the Hermitian condition, and we would show that this operator is Hermitian. So, the way we did in the previous case for the linear momentum operator, we take out the constant from the integration, out of the integration, and we are left with psi star d square psi divided by dx square dx. Now, again we will use the integration by parts here, but here my u is psi star and v is not psi, rather d psi by dx. If I take v as d psi by dx, then this term becomes u multiplied by dv, because one more differentiation of this function v gives me d square psi by dx square. So, since I have already defined u and v, I will do the evaluation of this term I would evaluate this term here. So, I have minus a square by 2 m. First the part is u v. So, psi star v is d psi by d x, and I have to evaluate these two terms, the product of these two terms at the limits minus infinite and plus infinite minus I v d u. So, v is d psi by d x and d u is d psi star by d x. Again, when I look at this, the first term psi star d psi by d x, I have to evaluate these two terms at minus infinite and plus infinite. I use the same argument that the wave function, if it is an acceptable or say if it is a well behaved wave function, then it must vanish at minus infinite and plus infinite, and also its first derivative should also become 0 at minus infinite and plus infinite. So, therefore, this term is again 0 and I am left with this minus and minus sign becomes plus sign h square by 2 m Now, this is still not the final form of the expression that we would require to show kinetic energy operator is summation, but I would actually leave this derivation right here with a request for you to continue this derivation to show the right hand side of the Hermitian relation. Everything that you need to do this derivation we already have discussed. So, therefore, it must not it would not be difficult for you to continue this derivation, and at the end you should be able to show that kinetic energy operator is also a Hermitian operator. Next, what we would do is that we would discuss some important properties of Hermitian operators. To do that, let us consider that I have an operator A, which I am calling it an let us suppose it is a Hermitian operator, and suppose psi m is an eigenfunction of this operator with an eigenvalue given by as a m. So, since I m is an eigenfunction of operator A with an eigenvalue of a m, I can write down this eigenvalue equation, and similarly psi n is another eigenfunction of operator A with an eigenvalue of a n. If we have to, I want to write psi m star A psi n d tau, since operator A is Hermitian. So, this is over all space minus, it can go to from minus infinite to plus infinite. I would leave this limit. So, if I have to write, since A is a Hermitian operator, I can write down this I know, because this is the definition of any linear operator to be called as a Hermitian operator. But psi n is an eigenfunction of A. So, what we would do is that we use this when operator A acts on this eigenfunction psi n, I know it gives me a n psi n, and in the right hand side when I see operator A acts on psi m, I get a m psi m I simplify both left hand and right hand side, since a n and a m are eigenvalues. So, which are constant. So, therefore, I am bringing them out of my integration. And if you see, I can take this right hand side to the left hand side and make them equal to 0. I have this expression now in my hand. So, I see there are two terms, multiplication of two terms, and that multiplication is 0. I consider case 1 where m is equal to n. When m is equal to n, so a m therefore becomes essentially a n. So, here also psi m star becomes psi n star and psi n remains psi m, but we already have seen this term. What is it? This suggests that as if we are trying to normalize. So, this both indices are n. So, if we as if this is actually the normalization condition. So, this value must be finite, because if wave function is a well behaved function, then I must be able to normalize it. It should be square integrable, and the value of this integration should be finite. So, since this is finite, so then therefore, this quantity has to become 0. So, that suggests a n is a n star, and this is possible when a n is real. This is actually not surprising, because we have already seen that we derived the condition for Hermitian operator by the fact that eigenvalues are real, but this also tells us that if if we have an Hermitian operator, the eigenvalues of the Hermitian operators are all real. Then we continue our discussion for the case when m is not equal to n. So, when m is not equal to n, so therefore, a n is not equal to a m star. So, this term cannot be 0. So, therefore, the second term is 0. Of course, we are assuming that the eigenvalues a n and a m are necessarily non-degenerate, or they are not equal, but then there are cases where the degeneracies are there. We would not go into that discussion. For our discussion, it is sufficient to see that if m is not equal to n, therefore, a n and a m are two different eigenvalues. So, this quantity is not 0. So, therefore, the second term must be 0. So, if m is not equal to n, so I see psi m star should be 0. So, this condition, when I see the overlap of this, is actually called an overlap integral. So, overlap of two different functions psi n and psi m star. So, the overlap is 0. When this condition is satisfied, we say psi m and psi n are orthogonal. So, we see that the eigenfunctions of any Hermitian operator are orthogonal. We already saw that the eigenvalues of Hermitian operator are real. Now, we see that eigenfunctions of Hermitian operator are orthogonal, but we also know that we already have normalized these wave functions psi n and psi m. So, the psi m and psi m are already normalized, because we know that if we have a well behaved function, we can always normalize them. So, these two conditions together, that when the wave functions are orthogonal and they are individually normalized, when these two conditions are met, then the psi m and the psi n, or these wave function, are called orthonormal. This orthonormal is a new phrase which tells that two functions, if two functions are called orthonormal, that means they are individually normalized and their overlap integral is 0. We will make some generic statements to that effect. We would say that we have psi m star is 1 when m is equal to n, and this is 0 when m is not equal to n. When m is not equal to n, then they are orthogonal. When m is equal to n, they are essentially normalized. So, together they are called orthonormal. So, this expression even in a shorthand, this is also given as a Kronecker delta. It is a delta function, delta m n. So, delta is a Kronecker delta. So, delta m n is 1 when m is equal to n, and this is 0 when m is not equal to n. So, in this present discussion, we saw that there are two important properties of Hermitian operator. First, the eigenvalues of this Hermitian operator are all real. The second, the eigenfunctions of a Hermitian operator are orthonormal. When I say orthonormal, I mean they are orthogonal to each other and they are individually normalized. So, these are two important properties of Hermitian operator. After discussing these two important properties of Hermitian operator, we will now look at yet another property of Hermitian operator. The eigenfunctions of this Hermitian operator, we saw that they are orthonormal. Now, there is another important property is that the eigenfunctions of Hermitian operator form a complete set. The eigenfunctions of Hermitian operator form a complete set. So, there already we know that orthonormal. So, the eigenfunctions of Hermitian operator form a complete set of orthonormal functions. Now, we will spend some time in discussing what do we mean by a complete set. If you remember, we saw that when we are deriving the eigenfunctions of linear momentum operator or angular momentum operator, we actually were getting a series of eigenfunctions and a series of eigenvalues. In oftentimes you would see in most of other cases, when you did obtain an eigenfunction, you get many eigenfunctions. In fact, so if the operator is Hermitian, you are going to get a complete set of orthonormal eigenfunctions. When I say a complete set of orthonormal eigenfunctions, suppose I have an operator A which is Hermitian and I have eigenfunctions as f1, f2, f3, so on and so forth. Correspondingly, I have eigenvalues as a1, a2, a3 and so on and so forth. So, where I am satisfying a f n is a n f n. If operator A is Hermitian, then all these f1, f2, f3 and so on and so forth, or in shorthand I say set of fi's, these eigenfunctions they form a complete set. When I say complete set, I mean that using these eigenfunctions fi, I can express any other arbitrary function. So, psi is any other arbitrary function which follows or which obeys all the limiting boundary conditions that these eigenfunctions of this operator follow. Any arbitrary function can be expressed as a linear combination of this eigenfunction, this complete set of eigenfunctions. So, where f i's are my eigenfunctions, they form a complete set. They would form a complete set if I can show any arbitrary function psi as a linear combination of these eigenfunctions f I, where the C I are the coefficients that I have to determine for a given arbitrary function. So, that means, if I take psi as one arbitrary function, I would be able to express psi in terms of these f i's. If I take yet another function, suppose let us say psi 1, I also, and it follows this arbitrary function also follows the boundary conditions that the way eigenfunctions of operator A follow. In that case, even psi 1 can also be expressed in terms of f i's. If I take another arbitrary function psi 2, that also can be expressed in terms of this complete set of functions f I. How would psi 1, psi 2, psi 3's definition be different? So, they will be different in terms of these coefficients. So, when I express psi I would have a particular set of coefficients of f I, and when I have psi 1, I would have a different set of coefficients for corresponding to eigenfunction f I. But in principle, I can define any arbitrary function psi as a linear combination of this complete set eigenfunctions of Hermitian operator. The important question therefore lies is that what is the value of psi, Ci, the coefficient. And in today's class, just to remind you, we discussed some important properties of Hermitian operator. We also showed that how different quantum mechanical operators are Hermitian, and we saw that the important properties of Hermitian operator are that the Hermitian operators have real eigenvalues and their eigenfunctions form a complete set of orthonormal set. In our future classes, we will continue our discussion. Thank you very much.